Okay, on to the fifth speaker now, and I have great pleasure in introducing to you a colleague of mine from CSIRO, Dr. Nico Adams, and he's going to speak on mind and manufacturing, new ways for an old industry. So we're getting quite practical and applied in this one. And Nico is another one of those people who I mentioned here today who's made vast leaps in their career, because he read chemistry at the University of York and subsequently worked as a research chemist in the Netherlands at DSM Research, and later he worked at what is now Millennium Pharmaceuticals in the area of high throughput synthesis and screening of olefin polymerization catalysts. In October 1999, he joined the Inorganic Chemistry Laboratory at the University of Oxford, where he received his PhD in chemistry. He left Cambridge to take up the position of project leader, polymer informatics at Eindhoven University of Technology and Dutch Polymer Institute before returning to Cambridge between 2006 and 2011 as a research assistant, associate research associate. At that point, he was recruited as a senior research scientist at CSIRO, where he leads some of CSIRO's materials and manufacturing informatics efforts. Continuing the theme of our speakers having huge leaps, he's moved from chemistry all the way to manufacturing and informatics. In his spare time, he develops ontologies for relaxation. I don't know what that means, actually. And he has an interest in Western and Chinese calligraphy. Recently, he started learning the cello, and apparently it's driving his neighbors crazy. The name Nico is the short form of the Greek name Nicholas, or Nicodemus, in ancient Greek, meaning victory of the gods, and a victory of the people, sorry. And I can reliably inform that this is the 22nd most frequent name for boys in Austria. Over to you, Nico.
Oh, excellent. So when I changed from chemistry, or after I told one of my friends who was also a chemist that I was going to change from chemistry into computer science, he looked at me and said, well, you know, computer scientists are a bit like noble gases, they expand into every available space. And he was completely right, and so therefore today I wanted to talk to you about informatics and manufacturing, and in particular the application of the mind to matter, to transform it, to bring new things into existence or to change existing things, and how the mind and for mind read, and I know this is a bit of a tenuous link, but read information, read data, read decision making about information and data influences this manufacturing. Now, historically, as you look over the last couple of hundred years, there have really been, if you will, two seismic shifts that have propelled humanity forward. The first one was the Industrial Revolution, very clearly. Now, you can subdivide stages of the Industrial Revolution if you want. So it all started at the end of the 18th century with the invention of the steam engine and the spinning jenny, and of course the Luddites happened at that stage as well. 100 years later on, electricity became available as a standard tool for production, and steel in particular became available. That caused another huge leap forward for industry. And then finally, not long ago in the 70s, when manufacturing was computerized, when computers took over control of manufacturing equipment and manufacturing machines. The other big step change that's happened very recently, of course, is the arrival of the internet. And the ability that the internet has given us to, at vast scales and very quickly, produce and exchange data and information. And what's happening today is that, as a matter of fact, these two developments are blending together in what's sometimes known as the Fourth Industrial Revolution. And this is really what I want to talk to you about. And my talk is really in two parts. I want to give you a bit of a feeling for what this fourth industrial revolution is what it could look like in the first part, and then in the second part, I actually want to take apart for how we are doing in Australia. How are we just waiting until everybody else has done it again and then buying off the shelf, or are we being sort of somewhat more proactive? And if we want to be more proactive, well, how do we get there from where we are? So that fourth industrial revolution is sometimes been described as the emergence of cyber-physical systems. And really what that means, it's jargon for families of, as you call it, computational agents, let's call them computational agents or computational units, collaborating together to regulate the physical world. And to make that happen, really, there are a number of technologies that are required. So there are things like the underlying enablers. There is cloud computing. There is fast data analytics. And Jörg has given you basically an introduction to what data analytics, and particularly for the new type of manufacturing, could look like. There is the semantic web, or semantics and general knowledge and learning, artificial intelligence, again in the way in which Jörg has described, to enable machines to understand the world, not just in absolute terms, but also probabilistic terms, and then make decisions about them. And finally, there is sensor technology. Now, all of these technologies have been in development for long periods of time. None of them are particularly new, but the fact that they're all coming together now, and the reason that they're all coming together is simply one of technological maturity, and the other one is just declining cost. It makes sense to put them together. So you've seen these graphs 1,000 times probably, but if you look at the cost of compute power, or sorry, no, this is data storage costs and how it's declined. Well, if you wanted to store a gigabyte of data in 1992, it cost you some on the order of $600. Now it costs you about 3 cents. Similar thing is true for compute power. $222 per million transistors in 1992, 6 cents in 2012. Cost of bandwidth, we're doing quite as well as that, and there are problems in that in itself. But no time to go into those. But you also see similar pictures with sensor technologies and a lot of all these other technologies that I've been talking about. These are kind of all coming together now into or you can start to blend them together into these cyber-physical systems, and in many ways these systems do very similar things to what humans do when they make decisions. The systems can set objectives. They can perceive states or the status quo of the world. They can interpret, judge, and act on them, and they can control their actions. Now, in this fourth industrial revolution goes by many names. In Germany, which is probably the country that's making the largest investment into these types of systems now, the German government has just announced a digital agenda. They're literally trying to completely revamp their manufacturing industry into digital manufacturing, into smart factories, into completely reconfigurable factories that allow you to make mass customized products. It's called Industry 4.0. In the United States, GE has been pushing a very, very similar concept, and they call it the Industrial Internet, and because, of course, this is our own, to do our own thing, we call it iManufacturing, or informatics-enabled manufacturing. But roughly, we're all talking about the same sort of stuff. So let me unpack what that looks like for you a little bit more. One of the first key enablers for this new industrial revolution is sensing, and sensing, of course, is everywhere. If you look at your mobile phone right now, these are the sensors that you have in your phone right now. As a matter of fact, you guys, if you carry a smartphone, you're an internet-connected agent. Your movement is being monitored, whether you're sitting down, or rather whether you're sleeping, lying down, or standing up is being monitored by the gyroscope. There are proximity sensors. We can determine whether it's light or dark. We can measure at which altitude you are. And you may have seen Apple has announced their smartwatch recently, and that smartwatch will contain things such as temperature sensor to give you skin temperature, humidity sensor to determine how much you're sweating, and so on and so on. And from that you can derive all sorts of health parameters. As a matter of fact, in many ways, a smartphone is already a perfect sensing agent for for manufacturing, because you can attach smartphones and these things are internet connected, they've got sensors which are tiny, you can connect them to your manufacturing equipment and you can get an awful lot of information about your factory and its operation from them. Now, sensors come in all shapes and sizes. Here's another example. This is from CSIRO research. So Paulo de Souza and colleagues up in QCAP in Brisbane have developed a tiny little sensor. This is an RFID sensor with its own power supply. It's 2.5 by 2.5 millimeters. The battery lasts for weeks and weeks and weeks, which you can attach to the which you can attach to the backs of honeybees, and you can follow their flight around Australia. That was done to determine the spread of a particular bee disease in Australia, and get a better understanding of how it spreads and why it spreads. But there are many industrial applications of this. So we are working with companies that, rather than to track the objects that they make on a pallet basis, which is what many companies currently do, they would like to be able to track individual items through the factory so that they can better optimize the manufacturing processes using, again, these types of analytics that Jörg's been talking about, and they can't currently do this, and so this sort of sensing technology is going to become very important. So now once you've got an object sensor up, then what you do is you take that object and you connect it to the internet. You use the internet as a communications platform which has been proven to work at scale, we all know that, to exchange that data. Now, for consumer terms, what that means is that your washing machine has just detected that you've loaded it up and that you really want to do some washing, but it can talk to your power plant and it can get some pricing information about electricity, and it can get some information about the state of the grid, and it can determine itself when it switches itself on to optimize the situation for you, i.e. to save you money by, for example, doing the laundry when it's most cost efficient, and to optimize things for the power plant, which will not just talk to your washing machine, but to all other washing machines on the grid, which will also have a notion of what its capacity to produce power is, for starters, and in that way can make smart judgments how much power to put out, when, at what price, given what materials usage, for example, if it's coal mine, for example, in Australia. Now, these networks in themselves can become nodes in larger networks. So ultimately, this Internet of Things is going to be a system, and it's starting to happen now, where we have objects connected to the web. These objects are uniquely identifiable because they're connected and identifiable. They can talk to each other and interact with each other. They form little sub-networks of a larger network. So you have a system of systems that's slowly developing there, and that holds all sorts of interesting opportunities, but also some problems. So, for example, right now we don't even have the programming languages or technologies to program. Billions and billions of devices all influencing each other and interacting with each other. So some really interesting challenges there. However, just censoring something up and connecting it to the web isn't going to be enough to make this work. The next component that's crucially important, and Jörg has demonstrated beautifully, really is analytics. He's done my job for me. I don't need to tell you anything about analytics and what that could look like and will look like in the future. So I'm going to skip over that part, but just as one thought to bring it back to the theme of today, the mind. The types of analytics that we're going to be using really can probably be described in terms of human-computer symbiosis. Now, if you know anything about artificial intelligence, when the field started in the 60s, there were really two schools of thought. One by Marvin Minsky. Minsky basically said, okay, machines are going to become learning, they're going to understand it, or they're going to take all of us and they're going to become completely autonomous. The other school of thought was put forward by a guy called J.C. Licklider, which is this gentleman there, and he, rather than to believe in autonomous systems, proposed literally this symbiotic relationship where computers would actually do, in many ways, what Jörg has been describing. So this is a text-heavy slide, but this is the original an excerpt from the original paper where he put the symbiosis hypothesis forward. And he is arguing that what computational elements or computational functionality will do is it will transform data, plot graphs, cut the cake in whatever way the human operator specifies, or in several alternative ways if the human operator is not sure what he wants. So there are Jörg's three possible answers to the question. There's the pro and con, if you will, in the discussion system. The equipment will interpolate, extrapolate, and transform it. It will convert static equations and logical statements into dynamic models. Again, here's the dynamic models, learning the probabilistic reasoning that is now starting to happen, so that the human operator can examine their behavior. Notice it comes back to the human operator in the end. In addition, the computer will serve as a statistically inferenced decision theory or game theory machine to make elementary evaluations of suggested courses of action whenever there is enough basis to support a formal statistical analysis. Finally, it will do as much diagnosis, pattern matching, and relevance recognizing as it probably can. Again, Jörg has just demonstrated. These are the types of capabilities we're going to be needing to make this Internet of Things work, and you see that Licklider's vision is actually starting to happen thanks to IBM. So now, if you take that scenario where you've got every object or where you have objects that can produce and consume data, that can communicate with other objects via communications platforms such as the Internet, coupled to fast analytics, and you apply that to manufacturing, what can happen? Well, here's what McKinsey, at least I happen to agree with it, thinks typical applications are for a sort of scenario like this in manufacturing. It breaks down really roughly into well, they only talk about two areas. I will suggest to you in the following slides that there's actually a third area, but it breaks into two super types of applications: automation and control, and information and analysis. Take automation and control. Process optimization is relatively easy to understand. If you can track what your factory is doing, if you know where your raw materials are, you can, using just relatively simple analytics, very quickly and process models, quickly determine inefficiencies in your factory, and then combine it with robotics and other things. You can adjust your workflow, making some savings. What's more interesting are things like complex autonomous systems. We have had a situation at a large aircraft manufacturer in the States a while ago where one of their workers was killed when other workers on a hangar moved a plane. The worker was in the path of the plane and didn't realize he was in the path of the plane. So now imagine the situation. You have a computational system. The worker is censored up because he's got his mobile phone with him. There are sensors on the plane. People know where in the hangar the plane is. If your environment is changing, if you can combine that with real-time mapping, then you can get a picture of where objects are in which pieces of space in real time at any one time. And then you bring in the analytics on top that do future state predictions, i.e. you don't just do one inference, you predict the whole spread of outcomes of the situation, and then determine which one the most likely is. And if the determination has been, well, this guy is likely to get run over in X number of seconds if he doesn't move out of the path, you can send an alert either to the worker, again via his mobile phone or some other technology, or to the airplane or to the airplane operators, and so on. So this is a typical scenario. Well, situational awareness and sensor-driven analytics sort of goes into the same, roughly into the same area. The one thing that McKinsey didn't talk about, which I think is in many ways even more exciting opportunity, is what we like to call servitization. It's this notion that as a manufacturer you make a physical object and then in abstract speak you wrap a digital layer around that physical object. Now what forms that would take, you can already see in very, very crude terms in the consumer space. Take your fitness trackers, for example, be that your Fitbits or your Apple Watches or your Samsung Watches, whatever. You've got such a situation. You've got a manufacturer who makes a physical product, namely the Fitbit that you carry on your wrist. Because that thing's got a sensor in there, and because it's connected to the web via your phone, you can build a digital service around that data, which is the smartphone application at the moment on your phone that tells you, well, you didn't walk enough today, or you didn't sleep for long enough, or you need to drink more water, or something like that. In the manufacturing space, service models become more exciting. So one of the most exciting things at the moment are, for example, condition-based maintenance or uptime guarantees. If you take something like aviation, for example, right now, most failures in aviation are caused by defects in either mechanical defects or electrical defects that only show up once you're actually usually starting to get off the ground. If you could sensor up your plane to monitor its state at any one time, and you can probably predict that it's going to fail sometime in the future. And as a matter of fact, this is not a hypothesis, and you can save an awful lot of money to the airline in terms of costs associated with delay and repair, but also an awful lot of inconvenience to your passengers. And that this isn't just hypothetical. Hypothetical scenario was actually just shown 2 days ago by a blog on the blog post on the Harvard Business Review, which talked about a trucking company in the States actually having gone down that path. They have censored up the engines of their trucks. They constantly monitor the engine, the performance of the truck. They send it back to headquarters. They analyze that data, make it available to an operator via a dashboard, but also do future state predictions so that they can actually predict before the truck is going to fail. In the moment in which they make such a prediction, they will send information about possible failure modes of the truck to the nearest garage that the truck is close to, alerting them to what might be wrong with the truck and directing the truck driver, again remotely, to actually go to that garage and have the truck fixed. This stuff is happening now. Here's another example. This was a while ago in the Wall Street Journal. BASF, together with Siemens, I think it was, has built a shampoo and soap factory. It's a demonstrator factory where everything, or every product the factory makes, is customizable. The scent of your shampoo, the hand feel of the shampoo, the color of the bottle your shampoo comes in, down to the screw cap. And this is another thing that these types of applications, objects connected to data and to each other, enable. It is mass customization of products. And the one thing that we're in Australia, and if you've all seen the news, where we really don't need to compete on with Asia is mass production. China is ideally set up to do mass production. India is ideally set up to do mass production. We won't compete. However, where we can compete are high-value-add, high-customized products, because this is what we are ideally set up to do, and this is one way to do this. So, what's the economic impact of the Internet of Things? Well, again, McKinsey reckons that it's going to add, by the next decade, somewhere between 2.7 to 6.2 trillion US dollars annually to the global economy, and they reckon that again in about 10 years' time we'll have roughly about 50 billion connected devices. I want to show you some work in that space that we've done at CSIRO. The first one is very simple. We develop analytics and models as well. So here's one for coal supply chain optimization in the Hunter Valley. So we get data about where coal is. If you want to expand the supply chains, how do you need to shuffle it around optimally to reduce costs, to increase throughput, and so on. This is work done by Rodolfo Garcia Flores and colleagues in Clayton. However, we also do things like develop remote assistance systems. Again, imagine something fails, you can detect that it fails. If you can't get to a garage in time, can you actually help somebody remotely to fix a problem yourself? And here's some work. I want to show you a video in that space. This was again done by colleagues at QCut in Brisbane. And I let them speak for themselves.
Remote technology that allows a remote expert to assist in real time a field worker anywhere, anytime, all you need is an internet connection. So instead of calling the expert, trying to get their assistance over the phone, or instead of flying in the expert and that costs a lot to remote operation, you click a button and you have instant communication with your specialist. You're able to demonstrate with your hand what needs to be done. You know, what particular way you need to turn, for example, a knob.
Can you please use your touch to show me the side of the machine? There should be 3 connectors there. Can you reach it with the touch? I need you to disconnect the leftmost connector there. And, can you put it on this one? Okay, yes.
We initially designed it for the mining industry, but we also have a different form factor that allows you to just have a head-mounted system that you can adjust the way you want it, whether you're wearing prescription glasses, safety glasses, or whatever.
The worker is seeing the hand gesture of the expert, but also the expert can show some technical documents that are relevant to the workspace and do annotation on top of those documents. The technology that we developed doesn't need any training. Both the expert and the worker has audio headset, so they are able to speak to each other in real time. We have added a touch device to the worker unit. In addition to the camera and the touch, we have added a scanner so that the worker can use the tags in the workspace to retrieve information like technical documents, manuals, or instructional videos.
There is a wide range of applications for this technology, and the industry that would benefit from it include health, transport, mining, shipping.
We see tremendous value in using the remote guidance systems for manufacturing and assembly, training, maintenance, and emergency repair. With the remote guidance system, a single expert can assist multiple operators located at geographic separate locations.
All aspects of the network communication are secure. The connection, the communication between the expert and the worker can do that.
CSIRO has customized the systems to our needs, enabling us to do technical drawings and record the interaction between the expert and the operator.
It's important to have this recording feature so that the field worker, after being assisted by a specialist, can revisit the interaction that they had with the specialist. Second of all, it's important for the specialist because then they have a record of what has taken place. Instead of flying in the expert, and that costs a lot to remote operation, you have that expert when you need it, real time. It's like having the specialist with you in the room, in front of the machine.
So here we're only talking about the expert being a human being, but again, following on from Jörg's talk, now couple such a system up to, for example, something like Watson, and again, you can get significant augmentation of the human expert as well, and these remote technologies in combination with these information tools become incredibly powerful. Very briefly, here's another example. This is again a sensing example, but this is some sensing technology that allows you to get overviews. So I'm going to talk over it to map your environment in real time using very, very simple hardware. It's a handheld LiDAR scanner coupled up to a building that allows you to, for example, just by walking through it, map a building in real time and keep mapping it. And the LiDAR scanner is actually on top of that under the HUD, all of the HUD, and you can see it. And it shoots lasers everywhere. And the smarts really is not in the hardware, but it's actually in the software. It's from detecting how the laser beam comes back. It's a building up of maps of your environment from the detection of how a laser beam comes back. I've been out mapping with my colleagues once, and I tell you, it's a great deal of fun just to observe how people look at you when you walk, when you walk around. But what you end up with in the end are these point cloud models of buildings. And you see this was done in 30 minutes time. This is a whole building. My colleagues have mapped the Tower of Pisa and other things, but coming back to our airport example, our aircraft manufacturing example, imagine doing that on a runway in a factory where you get constantly updated real-time information about where things are. Okay. So again, we are seeing these technologies converging into something that's really quite exciting. That's starting to happen. We call it iManufacturing, but we've seen the opportunities, we understand them, but how are we doing in Australia in terms of how far along are we in terms of adopting these sorts of technologies, in terms of adopting ICT and manufacturing in general? And we've done a piece of work on that recently, which we've just published in a discussion paper. And the answer really is, it's a mixed bag. There are a number of issues that we have to solve in Australia before we even get to adopting these sort of very advanced technologies, or that many companies have to solve before they can even think about engaging in these technologies. And here's the first one. Companies in Australia are still incredibly bad at using even the most basic ICT tools. While most businesses, 91% of small SME manufacturing enterprises have internet access, only about half of those have a website. 55% of businesses can place orders over the internet, but only 28% of those that can place orders can actually receive orders over the internet. And these are not CSRO statistics, this is actually ABS, the Australian Bureau of Statistics numbers. Now, the manufacturing sector, as you can see, is doing a little bit better. There, 39% of SMEs with between 1 and 4 staff can receive orders over the internet, 81% for companies over 200, so there's clearly a size factor there. But if you're in the manufacturing business, once you've solved that, the next problem that you're faced with then is this. As you're manufacturing your good, and what that means is you're going from, across these functions, you're going from the specification and design of what it is that you want to make, to materialization, i.e. to actually making it, and then controlling your machinery as you're making it. There's this whole profusion of technologies and standards and whatever else that you have to buy into, and many SMEs actually have a really hard time deciding which ones of these standards to buy into. So a lot of companies at the moment do not currently even have the skills to go and look at their business or their business processes and to competently decide which ones of these technologies they should adopt. What that leads to is that they, for example, buy an enterprise resource planning system where really they needed a product lifecycle management systems. Product lifecycle management systems manage all the information associated with your product, like CAD drawings, like bills of materials, like which machinery you need to use it, and ERPs, enterprise resource planning systems, manage your business processes. Nothing to do with product management, but they buy one or the other, and then usually they add in a little bit of functionality because they all of a sudden realize, that's actually not what we wanted after having spent significant amounts of money implementing these systems. And then usually because they've wedged it on, that doesn't fit very well too. So Australian businesses currently are losing an awful lot of productivity simply because either they don't participate in even basic ICT technologies, or they have a tough time deciding which ICT technologies to actually invest in. Once you've solved that, the next problem happens. Here's a scenario that we've come across recently. There's a company we're working with. They're a supplier for the aerospace industry in the States, and when they get an order in from one of their customers, that order is emailed as a PDF. They've got a fully trained up engineer sit there and manually retype that order into their enterprise resource planning system. Now, that costs them, and they've allowed us to share this information because it's actually so telling. That retyping step costs them $120 an hour. They need 1 hour per order. They get 200 orders a month times 12, $288,000. It doesn't sound like that much, but it's a company that turns over $20 million a year at a margin of 10%. So $288,000 for retyping something is either 1.4% of your turnover or 40% of your profit for a data entry step, simply by having a human sit there. Of course, part of the reason this happens is that these orders are significantly complex and they require interpretation, again by a trained engineer. Machines are not very good at that at the moment, but again, do we have learning systems that can help and assist with that and actually automate the process? Really, of course, this business-to-business data interoperability, and this is what it should be like. You have an electronic order which gets sent digitally to somebody's digital systems that they use to manage their company, and then if they need to subcontract out to other companies, that subcontraction is also managed completely electronically, business to business. And we find that at the moment it is not happening. It is not happening for technical reasons, and it is not happening because of the unique cost structure of Australian manufacturing enterprises. Here's an example from the engineering data space. Even if you manage to exchange your business process data, most companies have a hard time managing to exchange the engineering data. This is a piece. This was made by Southern Tools, and this is a tool maker up in Melbourne that we're currently working with us. Again, they've allowed us to share this. They've designed this piece. This is a test piece. It was done by their supply chain 3 times from one CAD file. So they've given the same CAD file specifying the same piece to 3 different makers in the supply chain, and you've seen that they will turn out to be different. This piece, for example, has a chamfer. This one has no chamfer really, and this one has a sort of semi-chamfer. This one, well, they've all got holes, but this one has got bits stuck in the hole. This one has got sort of some weird rings around the hole and so on. And why is that? It's because CAD files, or CAD, there are many different CAD file formats, and the only thing that translates across perfectly across various software packages are the geometric specification of the object. But the geometric specification of the object are not enough for example, a CNC machine or a 3D printer to actually make the object. They also need to have metadata on the geometry, i.e. data about data, and which, for example, specifies that, well, this is supposed to be a chamfer, or this surface is supposed to be black rather than brown, and so on. And there are currently no data standards, and so that data doesn't translate across supply chains and information systems between businesses. And what it results then in is, for example, post-machining costs. In the case of Sutton, for example, if they need to post-machine any one of these devices, $250 an hour post-machining time cost because of non-interoperable information. Now, there's a uniquely Australian situation that makes this business-to-business exchange so very, very difficult, and that's got to do with the structure of Australian SMEs. What we find that in Europe and in the States, SMEs and their customers tend to standardize on the same information systems. They can exchange data more easily, and that's because European and American SMEs tend to be much larger than Australian ones, and they tend to make more money per customer, and they have fewer customers than Australian SMEs. In Australia, the situation is exactly reversed. We've got typically smaller SMEs. They make less money per customer, and they've got more customers than their European counterparts. That makes standardization doubly hard. You've got less money to invest because you're smaller, and you've got a bigger integration problem because you've got a larger supply chain. If you take that together with the fact that manufacturing is expanding globally, actually roughly about 3% per year, and that large OEMs are trying to de-risk their supply chains, i.e. they're less and less willing to do business with very small and medium enterprises, such as the ones that we have in Australia. Australian SMEs have a problem. The message that we get back time and time again is you Australian SMEs either start growing by buying each other or form virtual supply chains. And if you want to form where a number of companies get together in a virtual supply chain that act like one company, for that to happen, you need to have this business data exchange and this engineering data exchange working. And it isn't currently working. If it's not working, we cannot take advantage of international supply chains. So these are and here the business implications. As I said, for this particular aerospace supplier, we're talking about 40% of profit for a data entry step. And I just want to leave you with that last thought, just in case you thought this was boring. The Australian manufacturing sector turns over roughly about $400 billion a year. If the cost of non-business to business data exchange is 1.4%, if that was a typical figure, let's assume back of the envelope calculation, that's a loss of almost $5 billion annually to the Australian manufacturing industry. That translates into jobs. Even if that figure was widely out, say it was out by 80%, take 20% of that figure, it's still $1 billion annually lost to constrained manufacturing. These are really, really fundamental problems that we need to solve. Now, are there companies that are, and before we even get to Industry 4.0 and so on, are there companies that are operating in the space? Yes, but only very, very few, and they're only taking the first tentative steps. I'll show you one or two at the end. So how should we respond to that as a country? Well, from what you've probably seen, it's a bit of a journey, or we think it's a bit of a journey. The first thing is we need to lift or endow even the smallest and the furthest behind SMEs with some basic ICT skills so that they can lift their business performance. Once they have done that, then we'll probably try and get them into business-to-business data exchange. We're talking about supply chains in Australia where you have one company running on, say, a standard SAP system, and in the same supply chain you've got a company that manages the whole company on an Excel spreadsheet. How do you get companies with these different technology bases to exchange information and to talk to each other more seamlessly and reduce some of those costs? Once you've done that, now then you can start to get into this internet-connected manufacturing. And really what we need to do is we think we need to address three areas. First of all, skills. We've consulted with about 50 to 60 companies about how they see the impact of ICT, the internet, and so on in their business going forward. And the one thing that they've told us time and time again is we as manufacturers, we need skill sets at the intersection of classical engineering, manufacturing, computer science, and data science. Because unless we have those, unless we have those, we're not going to be making any progress. Those companies that we've talked to that are furthest along this ICT enablement of their companies that we've talked to tended to be companies that have mechatronics engineers in them because they have this background of engineering and computer science, and that's usually programming. Hidden costs, we need to remove these data interoperability obstacles, and we need to then again prepare companies to take advantage of these future disruptions such as the Internet of Things. So we're currently working at the moment on e-manufacturing. We're trying to build systems with a number of companies to get that the data exchange between supply chains going more cleanly, both for engineering data as well as for business data and for design data. But what we want to work towards is a situation where we don't just have data exchange, where everything that you do in your factory is data driven, where you design your project digitally, where you simulate your factory that you're going to use to make the project digitally. You then materialize your factory and your project and your product. The product is designed in such a way already that it can be, at the end of its life, disassembled and ultimately recycled again. All of that is data-driven design. And that really is what we call informatics-linked manufacturing. Now, to push that a little bit, in Australia we've teamed up with Meta, the Manufacturing Excellence Task Force, and we're just setting up an iManufacturing hub, which is really hubs are very trendy at the moment, a sort of collaboration of companies, leading companies that are interested in investing in that space and solving problems in that space. So if you're interested, come and talk to us. And literally, this is how this maps, and this is what the iManufacturing hub is going to do. We're going to address these three things to push people along that path here. Because we're out of time, I'm going to skip the Saturn Tools thing. That was just an application that we're currently seeing. But I want to leave you with a question and a challenge. Say we've got the industry, say we've got the Internet of Things in place, the industrial Internet of manufacturing is in place. How do you see this? It's a question to you. How do you see this evolving? What's the next part of the story? Or if you thought about this sort of stuff at all and something resonated with you today and you're going back to your businesses, what do you think is the next step you need to take? We'd love to hear from you. Please come and talk to me after the talk. There's my colleague Marcel Dick, who's also in the audience, who would love to talk to you about it as well. So Marcel is waving. Shoot me an email. We'd love to continue the conversation. In summary, this is what we're hoping to do for Australia and for our small and medium enterprises. And if you've got any questions, then we may have time.
Thank you very much, Nico. We have time for a couple of questions. Yes, one down here.
I'm just going to repeat the question. Basically, the question is, how secure is the sort of is digital information in general, right? Fundamentally, I think since Edward Snowden, we know. Okay, fundamentally, every computer, you just got to know that fundamentally every computing system can be hacked. Okay, it becomes a question of probabilities and a question of, again, is the difficulty of hacking into your system justified by the economic gains that I can get from doing so? Right? There's your security factor. If you can make it difficult enough so that it doesn't pay anymore, or the effort is just too large, you've got the security. Security is also relative to the application and the intended use of your data, so you're going to have to decide that on a case-by-case basis. There is no global answer other than that every single computer system can be hacked by the very nature of how computer systems work.
Yes, one over there.
Yes. Sure. What I should have said, just addressing that last point, for example, what I should have said, we have not just talked to aerospace suppliers, right? We also talked to furniture manufacturers, we talked to fruit growers, and so on. They have exactly the same problem, one of not just data transcription, but also data quality, data curation, and so on and so on and so on. And there's really no reason why computers, whether necessarily or not technical reason, why humans need to be involved all the time there, and why that couldn't be done by a computer system. Whether a regulatory environment in any particular sector forbids it or not is a separate question. But thank you very much for clarifying that. Again, as to weight of sensors, yeah, of course. I mean, look, the aviation industry is way ahead of virtually all other industries in the game. Right? But again, at the other end, most of Australia isn't even a basic internet user, and I guess that was the fundamental point that I was trying to make.
One last question? Yes, one.
Yeah. Sorry, I didn't catch that. Well, issues of trust are certainly involved. I have not looked at it from that perspective. I thought about it from that perspective, I have to be honest with you. So I have no ready answer for you right now. It'll probably take me a while to think about that. But thank you very much for the question. I'll certainly go away.
We better leave it there. I've got a book here about synchronized cows, speedy brain extractors, and more WTF. What does that stand for? Research. And and hopefully this will be able to drive the research. Thank you very much.